will create a coarse-grained amorphous structure. I will start creating a monomer, then a polymer. I will define the coarse-grain potential for my polymer. And once the amorphous structure will be created, I will also show you how to use the reverse mapping function that I was mentioning before to go back to a full atomistic description of the amorphous polymer. And finally, I will run a diffusion scenario that you find in J-OCTA. I will explain in a second with what a scenario is in J-OCTA. So the creation of a coarse-grained polymer starts with the definition of the monomer. I will create a styrene molecule by drawing using a 2D monomer modeler. We'll define the coarse-grain, as you see in the image, perform some fast molecular mechanics and molecular orbital simulations, for then use the results to create a polymer chain. I will need to run a molecular dynamics simulation to then use the results to generate coarse-grain potential, bonding and non-bonding, for my cognac CG modeler. Well, things, I will create a monomer. I can click on monomer, or I can go directly to the project, right-click, new, monomer, new. I need to give a name to my monomer. I will call it styrene. Monomer as monomer file F MOM extension. This is J-OCTA format. And this, what you see here now, is the 2D modeler. So I'm gonna build up the styrene molecule. I will use a 2D modeler, and then I will generate a 3D model. So benzene, I will drag and drop benzene in my white area. And then I need to add 2 carbon atoms. And this is already my monomer, okay? If I click in create structure, I will see the structure on the right, with all the hydrogen at its proper place. Now, this is the monomer, but I need to do something else. I need to tell J-OCTA where I want to attach the other monomer to create the polymer chain. To do so, I need to go here on term and add some termination. So I will add one termination on the carbon atom on one side and one termination on the carbon atom on the other side. So I will drag and drop the 2 terminations and connect them to the carbon atom. Now, if I generate the structure, I see that 2 of my atoms are yellow, which represent the termination. Okay, let's define then the coarse-grain of my model. This is a step that is necessary only if I want to perform coarse-grain simulation, obviously, and not full atomistic. I selected the 2 carbon atoms, right-click, CG group, create. I call this group 1, a lot of imagination. And I can now click on the benzene and do the same things. The same thing, CG group, create, group 2. So like this, I initialize, basically, I tell J-OCTA which grain I want to have in my coarse-grain model. Now I need to perform some action here on top, going from left to right. Actually, these 3 fast things needs to be done. So set a force field. You can choose among different force field. I will use GAF because, I mean, it's not important in this case because it's just a fast tutorial, but this type of force field works well with these kind of molecules, this kind of material. Save and close. I will perform very fast molecular mechanics. As you see, I'm not touching anything. At this stage, it's not even necessary, honestly. These are just preliminary calculation, okay, to get my relaxed structure, molecular mechanics, and then I will perform molecular orbital calculation to get the charge on each atoms. I will use Mosemi, which is actually an internal engine on J-OCTA, so it comes with the code, but you can also use, for example, Gaussian, so use an external code. These are the results, where you see here that you have a given charge on each atom. So this is done. My preliminary calculation on styrene monomer are finished. And now I'm gonna create the polymer using this monomer. To do so, I'm gonna go on the webinar project, right-click, new polymer, and I call this polystyrene. POM is the extension of the Polymer file. So now it's empty, so we need to tell J-OCTA which polymer I want. So before, I need to register a monomer. So I go on this icon, and what I'm gonna do is basically load the styrene monomer file that I created 20 seconds ago, and I press on open. Okay, and here it is. Drag and drop. And now we need to tell like how many repetitions we want of this monomer in our polymer. So right click, repeat, set, and I'm going to put 20. Just like this. And this is my now polymer. As before, I need to perform some steps and some calculation. I need to set the force field. These are just a few clicks. I need to remove excess charge in the system, just like that. And I will also perform a fast molecular mechanics calculation to relax my polymer chain, super fast. I can now, once I do this, visualize my structure. Okay, for now it's just a banana-shaped polymer chain. Now what I want to do is create my potential, CG potentials. To do so, before I need to perform molecular dynamics simulation. So go here, and if I need, well, I can choose among several engines. If I need, I can change my settings here and then press run. This is not going to take much, just a few minutes, but for the purpose of this webinar, I'm going to skip this and show you already the completed a project in which I already made this step, this molecular dynamics simulation, which is this one. So in this case, I already run MD. And what I want to do now with my MD calculation already made is to calculate the coarse-grained potentials, so the bonding and non-bonding. This is the first one. Even in this case, I already ran previously this calculation. It takes maybe 20, 30 seconds, but I already prepared it. And this is an important step because because this is an important step to basically create a coarse-grained potential for bond, angle, and torsion, so intramolecular interaction, basically. And here is the bond 1, 2, angle 1, 2, and torsion potential, coarse-grained potential. Same things needs to be done for the Lennard-Jones potential, so a non-bonding potential. As for the previous case, we already ran this calculation, and these are the results. Basically, you know, Lennard-Jones potential. These are the two parameters characterizing the Lennard-Jones potential, and so sigma epsilon for the pair 1, pair 2, and pair 3 in our model. Good. Okay, I went a bit fast in this step, but this is just a preparation for what comes next, which is the generation of my spaghetti-like structure. I click on create CG cognac input. Here you have create cognac input. So this is what you want to use if you use full atomistic description. In our case, we have a coarse-grained input file to create. So I click in here, and here what I have is the possibility of setting simulation condition, boundary condition. For example, I can decide, okay, I don't choose the size of the cell, but I choose the density of my material. And very important is the definition of the number of polymers that I want in my volume. So in this case, I put 30. So if I do create, Okay, I think we can overwrite it, I hope. The input file for Cognac is created. So this icon is now active, and if I click in here, voila, I have my coarse grain model for I put here 30 chains, 30 polymer chain made of 20 units of styrene. Once I created my input file, my potentials, and my input file for my C coarse grain polymer, next things I'm going to show you is how to create amorphous structure out of it. J-OCTA has an amazing function which creates the structure for you. It performs several calculations, and the user is completely free, as you will see, to change any settings. So once I run this calculation, I will finally have my amorphous structure. We are almost there, okay, because this is the starting point to then create my amorphous structure. And what I'm going to do now is to go here. The icon to create amorphous structure is on this side. Okay, this seems very complex because indeed you can do different things. You can set up this parameters, the settings for each of the steps that needs to be undertaken to create the amorphous structure, but you can also use the default one. Okay. In this project, I already created the amorphous structure. So in this folder, create amorphous 0, I have all the steps, all the output of all the steps that led to the creation of the amorphous structure, which I saved here. And if I double click here, now I see my amorphous structure. Finally, I will show you how to run a scenario, one specific one, a diffusion scenario in J-OCTA. So first of all, let's define a scenario. A scenario is a preset workflow that allows for sequence execution of actions, okay? So this is very useful because so far we've been doing step-by-step all the setup, all the simulations, while a scenario can perform complex and several actions for you at the same time, in sequence, let's say. In this specific scenario, which is called diffusion scenario, we will see that there are two sub scenarios, one for performing the calculations, and the other to then analyze the results and extract the diffusion coefficient. The diffusion coefficient is estimated from the mean square displacement of the target molecules. This is going to be the results of this run of this scenario. I will show this on polyisoprene, which is a commonly used rubber material. On the left, there is the mean square displacement result of the MD run, and on the right, there is the fitting to extract of the MSD to extract the diffusion coefficient. And I go to the scenario simple diffusion folder. Okay, this is a scenario provided by J-OCTA. Okay, so it can be tuned, but it comes out of the box. You can use it. This is one of the many scenarios provided by JSOL in J-OCTA. And you have these two, diffusion calculator and diffusion analyzer, which we are going to use soon to extract diffusion coefficient. But in the folder, you find also manual, as well as some samples that you can use to perform some test calculation, which is exactly what we are going to do today. We are going to diffuse oxygen atoms on this structure, which is polyisoprene. Okay, so it's always an amorphous structure. It's slightly different from the one we just created, and this came with this scenario. Okay, so let's go back to this diffusion calculator and run the scenario. I'm gonna click on run here, and I need to tell which is going to be my amorphous input. We said we're going to use this PI polyisoprene, amorphous structure. Okay. The directory, I'm going to change this one, and I'm going to use this one called webinar. And also which molecule we want to diffuse in our amorphous structure. We can create one, or we can use one from the database. In this, before I mention oxygen, so let's select the oxygen gas UDF file. And finally, the number of gas molecules that I want in this volume of polymer. Okay. Okay, override. These are the settings for the MD calculation that will be necessary to then get the diffusion coefficient. Last step, I need to select the engine, which is going to be cognac in my case, but you can choose also between BSOP and LAMPS, and the number of cores. I already performed this calculation previously, so I show you already the results that are in my work directory. So this is the input. As you see, J-OCTA constructed the system, putting these 5 oxygen molecules within my space where I have my polymer, and this is the output file. However, the output file is basically an MD dynamics. Okay, where you see how the oxygen molecules are diffusing in the system. Okay, then, but how to analyze these results? Because this is nice to see, but doesn't give you any number, basically. Well, for this, we need to use the next scenario, which is called diffusion analyzer. And, well, I just need to say which output I want and just press OK. Input gas molecule, well, he understands. He knows that I want oxygen. First record number and output file name to be used. So basically, out of the MD, and I can choose which step I want to include for the calculation of MSD. I leave the default one. Okay. And I can also choose here the range in step, in time, that J-OCTA will use to fit the curve and extract the diffusion coefficient. Okay, so this is the result. On the this one is the MSD, so the mean square displacement of oxygen molecule within my system. Here I have like around 2,000 steps I made before. And then what we want to do in this case to extract the diffusion coefficient is to take a linear regime, so kind of in this area, and perform a linear fitting, which is what we have already done in the next here. So you see here I have a range from 200 to 1,000, so a bit less than before. In here I said to J-OCTA, okay, fit a curve in this range. And the numbers of the diffusion coefficient, okay, is here at the bottom. So in the console are plotted the numbers, the final result for my calculations.